In this video, I'll cover the first half of the sample exam over chapters 7 and 8 for statistics. The first questions in this exam have to do with the central limit theorem. You need to know those words, central limit theorem. That's a very crucial theorem, very central theorem to all of statistics. And what the central limit theorem says is that if you make measurement after measurement after measurement and you average every single one of those measurements and make a histogram, that histogram will approach a bell-shaped curve. For this histogram, you'll have, I'll do a little one down here, you're going to have the frequency here, and you'll have all these averages here. Okay. And if you made the histogram, it will look something like this eventually, and it will approach a bell-shaped curve. A nice one, not something I drew like that. But the whole idea is that the histogram of the averages from multiple statistical studies, multiple samplings, this histogram will approach the bell-shaped curve as the number of samples that you take approaches infinity. And like I say, the operative words to remember are central limit theorem, something you have to take away from here. The second part says, what about the average? What about the middle of this bell-shaped curve? Well, this would be the average of the bell-shaped curve, the mean right in the middle. I can't seem to get the V's to go right with this pen. That average is also the mean for the entire population. Like I discussed in homework, this makes sense because if I took enough samples, I would eventually have sampled the entire population, so the average of that would be the population average because I would have tested the entire population. So basically, this holds in approximately, it holds in the limit. So this average right in the middle of the bell-shaped curve is also the population average. Also, as the size of the samples increases, this bell-shaped curve gets narrower and narrower. This just shows a bell-shaped curve, not the histogram. But this would be the relative frequency over here. So this will be a distribution curve, relative frequency, and here the sample averages, the sample means. Now on this curve, the mean for all of these curves is 64.4, and that is also the mean for the entire population, whatever the whatever the subject of the study was, 64.4. That's not a 7, that's a 4. Okay, now these curves get narrower and narrower. They get more narrow as the size of the sample increases. So if I'm sampling 25 at a time, I'll have this red curve, which is has a fairly large standard deviation. If I sample 50 at a time, the curve is narrower. As I increase to 100, the curve becomes more and more narrow. So if you're given a group of curves and you're given samples, it doesn't matter how many you sample, it matters how big the sample size is, and that's how you would order those curves. If you didn't know the 25, the 50, and the 100, you would say, in this case, you would have the fewest number of subjects or units that you are sampling. Here you would be sampling more at each time, and on this green one, you would be sampling the most for this example. Those would be all the questions for the central limit theorem. The next part has to do with confidence intervals. So the first question is just confidence intervals in general. And it says, using the information in the reference section, show the rejected tails for a confidence level of 90%. Mark the edges of the tails clearly. I'm going to go to the reference section right now so you can see what that looks like. For the confidence intervals, you're given this chart. Now, if you remember, for confidence intervals, you could have used the standard normal distribution in which you're looking for z-values. You could have looked for the t-values from the student's distribution, student t distribution, and also you could have been looking at chi-squared distributions. For the test, you only have to know the z distributions. You don't have to know the t and the chi-square. So here we have the table for z. This was in you had to write this in the homework, and also it's in the lecture on sample problems for chapter 7. So here we're looking at confidence intervals, and we even have the equation for it right here. And now, depending on the confidence level, there's different values of z alpha over 2. Remember, in confidence intervals, you take the alpha, and it's going to be alpha over 2 because you are because it's a two-tailed situation where you're rejecting both tails. Okay, so for the confidence level, in this case, say 90%, you find that z alpha over 2 is 1.65. And that's all you need to know for this particular problem. If you're given another number, of course, you'll have a different z alpha over 2. So for this problem, you will have a graph, a bell-shaped curve rather, with nothing on it. And you have to fill it in. So in this case, we found that the z alpha over 2 was 1.65. So we have marked that right here, 1.65 approximately, of course, and here would be the tail that would be rejected on the right, and there's also a z alpha over 2 equal to negative 1.65. That's right here, and this is the rejected tail on the left. And that's what's required for this. So for a confidence interval, you have certain values that you reject, and that would be the extremes, these two tails, and this would correspond to your interval. The next question is also a question about confidence intervals in general, and the question is, which confidence interval is larger? That should be an ER on it, larger. Okay, a confidence interval corresponding to a confidence level of 45% or 50% or 55%. Well, if you want to be sure, what does a confidence interval mean? It means that this is an interval about the sample mean in which you're guaranteeing, so to speak, up to some confidence level that the actual true value for the population lies in that interval. Well, if you take a great big interval, you're more likely to capture it. So if you want to have a larger confidence level, you need a larger, you'll have a larger confidence interval. So these two correspond to each other. The larger the confidence level, the larger the confidence interval. On the test, there will be one calculation for a confidence interval. Like I said earlier, you will only need to use the z values, not the t and not the chi-squared, just the z values, and that will be given in the reference section. So you'll have some scenario. In this case, let's say the wait time for the DMV, the average wait time for a large study. Right, okay, previously the average wait time was 45 minutes, right, with a standard deviation of 4. So someone studied many DMVs and came up with an average wait time of 45 minutes at the DMV with a standard deviation of 4. Then a new study is made looking at only 16 DMVs, and they found that the wait time for those was 47 minutes. So the question is to find the confidence interval about this 47, about this new average for some confidence level. So in the reference section, you'll be given the confidence level, in this case 99.7%. So when you look at the reference section, you can find 99.7%, you'll find the value for z alpha over 2, and you'll find the corresponding formula. So for this example, here's your 99.7. You find that z alpha over 2 is 3, and here is the formula already written out. This is the formula for confidence interval. It says that the population mean, which is mu, lies between the sample mean minus 3 times, in this case 3 because of the confidence level, 3 times the standard deviation divided by the square root of the sample size. In this case it was 16. Easy to calculate numbers, so used on tests. So it's the population mean lies between the sample mean minus 3 times sigma over the square root of n, and the sample mean again plus 3 times sigma over the square root of n. So this is the interval. I should have marked those in different color. Okay, the green, which now obscures everything. Okay, the, I'll put it underneath here, these values make up the interval, and you're saying that with 99.7% confidence, the true population mean lies between those two values, lies in that interval. So all you have to do this test problem is find the confidence level that's specified 99.7. From that, you will have found this formula, and you're going to take that back to the other page and plug into that formula. So here's a calculation. Should write down here what it was before. Okay, the sample mean was 47. The population standard deviation was 4, and the sample size was 16. So substitution yield that first line there, you work out the arithmetic, and you find that the interval is 44 to 50. So with 99.7% confidence, the true average wait time at the DMV lies between 44 and 50. Now, some tests are not good tests, and the actual population mean doesn't lie anywhere in that interval. So the question is, does this confidence interval actually capture the actual mean wait time at the DMV? And in this case, yes, because in this case, mu was 45, and 45 does lie in that interval.